A warm welcome to everyone. Today we are going to see isomerism in our coordination compounds. And in this class, we are going to see a certain special kind of isomerism known as geometrical isomerism. We know what are isomerism, right? We have studied that in smaller classes. And two or more compounds are having same chemical formula. That means the number of uh, atoms present in them are same, but they differ in the atomic arrangement. And that phenomenon is known as isomerism. And because of this difference in spatial arrangement, these isomers will have different properties. One or two chemical or physical properties will be different for this isomers. So we are seeing isomerism in the case of coordination compounds. Generally, for coordination compounds, there are two types of isomerism. First being the stereoisomerism, second is structural isomerism. The difference between stereoisomerism and structural isomerism is as given here. Stereoisomerism is for compounds that are having same atoms and same sets of bonds. The type of bonds and the atoms that are forming are same, but the only difference is the orientation of these bonds or spatial orientation. How these groups or atoms are arranged in space is different for stereoisomers. Now coming to the structural isomerism. Structural isomerism is such an isomerism where the isomers have same molecular formula, same atoms, but they differ in the bonding patterns. The type of bonds or set of bonds in structural isomers will be different. So atomic organization and bonding is different for structural isomerism. Stereoisomers will have same kind of bonds and atomic organization, but how that is arranged around a metal is different for stereoisomers. So in structural isomerism, there are two types of isomerism known as geometrical isomerism and optical isomerism. And in stereoisomerism, I'm telling about stereoisomers. For stereoisomers, two types of isomerism are possible: geometrical as well as optical. So in today's class, we will see what is geometrical isomerism and different types of geometrical isomerism. So geometrical isomerism means the type of atoms, the number of atoms or number of groups and type of bonds are equivalent for isomers, but the only difference is how they are arranged around the metal. So for a planar molecule, this type of isomerism is possible, geometrical isomerism known as cis-trans isomerism. That's when for planar coordination compounds like ML2, X2 type, this is the geometrical isomers possible. Here, around the platinum atom, these two types of arrangement is possible. In one, we have same atoms are close to each other. Here, chlorine and fluorine are close to each other. NH3 and NH2 are closer to each other. That kind of isomer is known as a cis isomer, where the similar groups are placed together. They are in space. They are together. So for the other type of isomerisms, geometrical isomerism, trans isomerism, where the same atoms of same groups are opposite to each other. So this is an example for geometrical isomerism for square planar complexes. Now coming to octahedral complexes. This trans isomerism is like this. For example, this is a octahedral complex of compact. So here also cis isomer and trans isomer are there. Cis isomer means the same atoms of same groups. Here we are considering Cl, chlorine. So chlorines, both the chlorines are closer to each other. That is a cis isomer. And then the chlorine is opposite to each other. This is known as trans isomerism. This is an example for cis trans isomerism for octahedral complexes. This is square planar. This is octahedral complex. Now coming to these kind of complexes where heteroleptic ligands are used. Heteroleptic we have studied in earlier classes. What is this? Heteroleptic. That means a single ligand is coordinated to the metal via two sides. Example for such a ligand is this En. En means ethane 1,2 diamine. NH2, CH2, CH2, NH2. This is abbreviated as En. Both the nitrogens can be used for coordinating to the metal. So in such cases where heteroleptic ligands are used, the isomerism, this is trans isomerism, can be shown like this. Where in molecule where the same kind of atoms or groups are closer to each other is known as cis, whereas when the same atoms or groups are opposite to each other is known as trans. So we have a general idea about cis and trans isomers for square planar and octahedral complexes. Also in the case of heteroleptic ligands. Now there is another kind of cis trans isomers known as Fax and Mer isomers. Here the complex is of type this ML3X3. Octahedral complexes of this type will show an isomerism in which one is called Fas, but the other is known as Mer. When the same groups are arranged in a cis fashion, that is known as fascial isomer, and when one of the same group, one among the same atoms of same groups is in a transposition. Here in the case, this NH3 is in a transposition with the other two NH3 groups. So this is known as Mer isomer or meridional isomer. Also, for square planar complexes of type M, L, X, A, B, we have three isomers, two cis isomers and one trans isomer. These are this metal A, L, B, X, and then metal A, L, X, and B. Here, this is isomer. This is also a cis isomer. This is a trans isomer. Here we are assigning the cis trans configuration based on by fixing the position of one ligand, and with corresponding to that we are saying one is cis isomer, other is trans isomer. With this we are coming to the end of this class. I hope everything is clear, and we will see the next portion, that is the stereoisomers in next class. Thank you for watching.